So today we're going to cover 10.7 to 10.9, which is on the Gauss theorem or divergence theorem of Gauss and the applications of that, and the Stokes theorem, covering 3 sections of the book. But of course, as you will see, my approach is totally different as usual. And in 10.7, we're going to introduce the triple integrals first. In the previous sections, 10.5, 10.6, we introduced surfaces and surface integrals. In this section, we introduced triple integrals over a region of space and give a new definition of divergence of a vector field. This is not the approach of the book. I have my own approach, which I learned through years. I think it's a lot better to understand, easier to understand. Then we introduced divergence theorem, that is transformation between a triple integral over a region of space and surface integral over the boundary surface of that region. So this is a very, very important theorem, and you see the applications later. From calculus, the triple integral of a scalar function, f of x, y, z, over a region of space t is defined as the following. We divide the region T into a large number, which we call N, of small boxes of volume delta V K, which has dimensions delta X K, delta Y K, delta Z K, multiplied together comes delta V K. K goes from 1 to N, the number of cells you have. We call the largest of delta X, delta Y, delta Z for each K as the norm of delta V K, denoted by double vertical lines, norm of delta VK, right? We choose a point in each box. We call it XK, YK, ZK, the coordinates. And we add all the values of F evaluated at that point times the volume of that cell, and take the limit as the limit of the summation as n goes to infinity, and means the number of cells goes to infinity and each cell shrinks to 0. If this limit exists, we call it the triple integral of f over the region T. This is the normal definition of integral in calculus. So in notations, we call it like that, triple integral over the region T of f of xyz dv. And then we can write dv as dx, dy, dz. And this is the definition: limit as n goes to infinity of summation from over k from 1 to n of f evaluated at each point in those delta vk's times delta vk. Similar to definition of integral in just one variable. All right, so this is the triple integral. We're going to use that. Is there any question so far? So this is just reminding you of the triple integral. All right. Now, a new look at the divergence of a vector field. So first, we defined the divergence in the last chapter, divergence of a vector field F, as del dot F, or this del operator, which we call it this inverse of delta. And we have 3 components: the partial derivative with respect to x, partial derivative with respect to y, partial derivative with respect to z, dot the field, which has 3 components, x, y, z, which call it F1, F2, F3. But if you do dot product the same way, it means that we take derivative of the x component with respect to x, plus derivative of y component with respect to y, plus derivative of z component with respect to z, which we write like this. So it's a scalar, without adding all these partial derivatives together. So this was the way we defined divergence before. Now we want to define divergence in a new way. which is very interesting. Now, because we know the surface integrals, we can have another equivalent definition of divergence of a vector field f at any point P in space. And we define it this way. We choose a small, simply connected region of space T containing point P. So this is a region of space that has point P in it. Okay? We calculate the surface integral of the vector field F over the surface S of the boundary of T. So this the region of a space is called T. The surface that bounds that region T is called S. And we calculate the surface integral of the vector field F that's present here over the boundary of T, which is S. So we write it like that. The surface integral over S of f dot n dA means that this is the normal component of f times the area element double integrate over the surface. This is the surface integral you're familiar with. So we take this surface integral and divide this surface integral by the volume Vt of t. So this V of t means the volume of the region T. So we divide that surface integral by V of t, and then take the limit of this quantity as t shrinks down onto P, so that the maximum distance d of t. So d of t is the maximum distance of all points of this region to point P. Then when that goes to 0, we take the limit of this quantity when d of t goes to 0. If this limit exists, we call it the divergence of f at point P, which has coordinate x, y, z. So we call it divergence of f, or del dot f at x, y, z, any point, equal to this surface integral divided by the volume and limit when the dimensions of that volume goes to 0. So this is maybe a weird way of defining the divergence. But personally, when I was in college, when I was studying physics, we had a junior course in electromagnetism. I remember the book that we were studying from was Rhat and Milford, written by Rhat and Milford, and they defined the divergence like that. And then I don't know if there was a proof of equivalence, and I saw the equivalence, and it went above my head at that time. Why do we define divergence like this, and what does it mean really? So I didn't understand it quite well by looking at it. So I remember sitting down and thinking about it for a while. What does it really mean? I'm sure it goes above your head right now. So if you sit down and think about it, and of course, with this lecture, I will help you to understand it more, but it takes some sitting down and thinking about it deeply and internalizing it. And you see that it makes a lot of sense. And when I did that, after that, I'd never had any problem with this definition. It was so intuitive for me, and it was so eye-opening. And that's why I think that all the books should start from that, instead of starting from this that is just purely mathematical and doesn't mean anything much. So as you see, the book that we are studying from, the Krasik, is working on that for divergence, and just mentions this at the end. I think we should start from this and work on this, and then you see everything falls into place. It's very, very beautiful. And that was really when I fully understood divergence, and also curl was defined similarly. And then from then on, I totally understand what divergence means and totally understand what curl means. It is some intuitive concept to me. So that's why I think it is better to do it this way. And I hope I can catch your attention. And if you don't understand it fully, I'm going to put the video on YouTube. You can watch it again and understand it, and you will feel the same way. And it's really beautiful. So this is the new definition of divergence of a vector field. From this definition, it is easy to derive the Cartesian representation this. So how this is equivalent to this, and vice versa. All right, so let's do that. Consider T as the small box shown in the figure with volume V of T, which is delta V. And here in this case, because it has dimensions delta X, delta Y, delta Z, the volume becomes delta X times delta Y times delta Z. We calculate the surface integral flux of the vector field F going out of this box when the dimensions of the box approach 0. So we are going to approach delta Y, delta X, delta Z to 0. And we did that before for calculating flow rate, but now we do it similarly here. The net flux of F going out of the box through the back and front faces is. You see, this is the front face. The back face is over there that you don't see it. And if you calculate the flux going out of these two together, is this. We did that before. The X component of F. Why is X component? Because X component is perpendicular to these two faces. The other two are parallel. They don't create any flux. X component of F evaluated at X plus delta X, means at this point, and of course Y and Z, times the area, which is delta Y times delta Z. So this is delta Z, this is delta Y, the area, times the X component of F that is evaluated over this surface, of course at this point, but because this delta Y and delta Z are small, there's not much variation of the first component or X component of F over the surface. So we can approximately say that the flux through this space is this F1, means X component of F, evaluated at this point, but then multiplied by the area. And then flux going into the box from the other side is the F, X component of F, evaluated at this point, not this point. This point dot times the area of that face again, which is delta Y, delta Z. All right, and then this is delta Y, delta Z. If we multiply by delta X, we get the volume of the box. So we multiply by delta X and divide by delta X. So we get this. This is the volume. And here we have F1 evaluated at X plus delta X minus F1 evaluated at X divided by delta X. And as you know, this is delta F1 over delta X, like that, times delta V. And if you do the same thing for the flux going out of the box through left and right, this is the left, this is the right. Again, you do the same thing. The second component matters here because the faces are perpendicular to the Y component, and that Y component evaluated at Y plus delta Y, which is, and X and Z, which is the corner that you don't see in the back over there, times delta X, delta Z, which is the face of that face, the area of that face, minus the flux going through the left face, which is this. So the second component, Y component, evaluated at this point, times the area of that face, which is delta X, delta Z. Again, we divide by delta Y and multiply by delta Y. So we get this. So that is delta F2 over delta Y times delta V. And for the top and bottom faces, we have the same thing, but this time F3 comes into play because the third component, the Z component, is perpendicular to the two faces. And then we have the same thing like that. So if you add all of these, you get the total flux of the field F going out of all the box. So the net flux of F going out of the box through all faces, that is the surface integral over the surface of the box, is approximately sum of all these three. So this, the flux going out of these, which is actually the surface integral, F dot n dA, is sum of all of these, and dV can be factored, and so we get that. So let's get rid of the rest of them. Now we have this. And then if we divide this equation by volume of the region, this is our region, the box, volume of that is delta V, so that's this. If we divide and then let delta X, delta Y, delta Z go to 0 and take the limit, we get limit of 1 over V of t in double integral, the surface integral of F dot n dA over this surface, as the dimensions of the box go to 0, equal to the other side when delta X, delta Y, delta Z goes to 0. And you see that these are partial derivatives of X component, Y component, Z component. So we have that. So this shows the equivalence of the two definitions of divergence. From this definition, you can get the other definition. All right? Does it make sense? Any questions? So you see that this definition is equivalent, but this is more intuitive. The new definition has the advantage of illustrating the divergence theorem that we're going to study next in an intuitive way, as we see. All right, so we're going now to basically derive the divergence theorem, or show the proof of divergence theorem. It is not a concrete proof, but it is an intuitive way of understanding the divergence theorem of Gauss. All right, so this is the setup. Consider a closed bounded region in space T. This is the bounded space, the volume, it is the region, three-dimensional region. It's called T, whose boundary is a piecewise smooth surface S. So this S is the surface of the boundary, and it's a piecewise smooth surface. Also consider the vector field F of function of x, y, z to be a vector function that is continuous and has continuous first partial derivatives in some domain containing T. Means that there's a larger than this, some domain that has all of T in it. In that domain, it has continuous, it is continuous, and it has continuous partial derivatives. All right, so this is the setup. Don't worry about it too much. Assume that the region T is subdivided into a large number of very small boxes of sides delta X, delta Y, delta Z. This figure shows the cross section of this region and the subdivisions in 2D. So we're only showing the two-dimensional cross section of that region. But these are all three-dimensional boxes. So we subdivide the whole thing into the small boxes. Focus on the shaded subdivision K with boundary SK. So we call that subdivision K. It has a boundary SK. It's a boundary, it's like a cube of that cell. And then the flux of the vector field F over the surface of this cell is what? This is the vector field, let's say, and it has it passes through the faces of this cell. And the flux going out is written as F dot n dA, a double integral over the surface SK. All right. From the new definition of divergence, this surface integral is roughly equal to the divergence of f at a point in that cell, which we call xk, yk, zk, coordinates of xk, yk, zk, times the volume of the cell delta vk. Remember, this was the definition. The double integral over any surface is the divergence of f if the volume is small enough. So take out the limit. If the volume is small enough, it is almost the same. So the surface integral becomes divergence of f at some point in that volume times the volume. All right. So we say this double integral, which is the surface integral over sk, is roughly equal to divergence of f at that point xk, yk, zk times delta vk, which is the volume of that cell. All right. So we have that, and then remember the what was that? The triple integral we defined. Triple integral of any scalar function dv is the limit of sum of f evaluated at that xk, yk, zk times delta v as the number of the cells go to infinity and each one shrinks to 0. All right, so we are going to add all of these divergences over the three-dimensional region T, okay? And we call it that so we can just this xk, yk, zk. So this three-dimensional integral, the divergence of f dv, is the limit of sum of divergence of f at a point in a cell times volume of that cell added together, all of these summations, and take the limit of that summation as n goes to infinity, and of course the dimension of each cell goes to 0, right? Because you understand that you can keep one of them large but set the number go to infinity. That's not the case. Each one of them go to 0. So this is the triple integral of divergence of f, which is like that. But this in this summation, this part is equal to that. So we can write that as limit of summation of all these surface integrals, right? Like that. So the triple integral of divergence of f can be written as this. So let's just work on this one, see what that implies. All right, so far so good. Any questions? All right, so now we want to see what is this quantity. But the flux of f through each face of cell k cancels with the flux through that face for the cell on the other side. So you see this, look at the SK, for example, that is this one. If you calculate the flux through all these spaces, it means the flux of field F going out of that total is, you can divide it into 6 spaces, right? The surface is 6 spaces. Each one has a neighbor on the other side. And this summation is adding all the fluxes going through all of them. Here it says the flux of F through each face of the cell cancels with the flux through that face, the same face, for the cell on the other side. This is more explanation. This means that for instance, the flux going out of the green cell through the right face is this one, which is, as we show here, if the field is this way, it is positive for that. Is the same as the flux through the same phase into the yellow cell, which is negative. So this flux through this phase, for this cell, it shows up as positive. For this cell, it shows up as negative. And if you add all the contributions, they cancel each other. The same for all cell boundaries within the surface. So for all of these boundaries of cells, each one cancels with the neighbor, unless you go somewhere that there's no other neighbor. Okay? And you on the surface S of the region T. So, so the sum of all surface integrals over all cell boundaries is equal to the surface integral over the exterior boundary S. All right, so all of these interior surfaces, they cancel each other until you get to the surface. So that this total summation becomes only the flux of F going through the surface. Therefore, triple integral of divergence of V becomes the double integral over the surface of surface component, the particular component of F over the surface, evaluated like that. And this is the divergence theorem of Gauss. So you see, using this new definition of divergence, it simply by intuitively gets you to divergence theorem. It will be a lot harder to prove this theorem using the other definition, which is what the book does. But I think this is a lot more elegant and more intuitive. That's why I think the book should do this way. I don't know why they don't. All right. And I haven't really, I don't remember any book that does it like that. But because I understood the definition of divergence this way, I see that it is very natural that you get divergence theorem. And I think maybe Gauss did it that way rather than the other way. I don't know. Okay, so this is divergence theorem of Gauss. So let's see what that implies. Remember that we had differential and integral forms of Gauss law. So we talked about the differential form of Gauss law. We said that divergence of E is equal to rho over epsilon naught for any charge distribution. When you have some charge density at some point in space, divergence of the electric field is equal to the charge density divided by epsilon naught. We talked about that before when we were talking about divergence, right? Now we can work on this and use this divergence theorem, see what we get. If we take the triple integral over the region T for any region, if we integrate both sides over the region T, we have this over any region T. We have triple integral of divergence of E dV equal to triple integral of rho over epsilon naught dV, right? Simple. But you see, this side is a triple integral of divergence of a vector field, which we can write it as double integral over the surface of E dot NdA. And on the other hand, this 1 over epsilon naught comes out, and triple integral of rho dV is what? Because rho is the density, right? At any point is the dq over dV, means the small charge that is in the small volume. If you divide dq over dV, it becomes rho. So rho dV becomes dq. And if you add all the dq's inside the region, it gives you total charge inside the region. So this side becomes a surface integral, and the other side becomes total charge, right? So surface integral E dot NdA is equal to total charge divided by epsilon naught. This is the integral form of Gauss law. So this is differential form, this is integral form. You can go from one to the other using the Gauss theorem. So the reverse argument is also possible because you can go from here to here easily. See, this is Gauss theorem from here to here. And for here, instead of Q, write triple integral rho dV. And then we say that because this T is arbitrary, this equation is true for all the regions T, then there's no way other than the two integrands be the same. So we can say that the divergence of E is equal to rho over epsilon naught. So from the integral form, we can go to the differential form and vice versa using divergence theorem, which is one of the important tasks of this theorem. All right. Any questions? So there's no surprise that all of this was done by Gauss, because I think Gauss understands this is the physics that he created, this is the math that he created, and then it goes from here to here and vice versa. All right. So let's do some examples. This was one of the applications of divergence theorem. Let's do some practical examples or some integration, see how they work. Remember, if we have this sphere, we talked about that. We can parameterize the surface of a sphere by this R as a function of theta and phi, R sine theta cosine phi, R sine theta sine phi, and R cosine theta for x, y, z. And theta goes from 0 to pi, phi goes from 0 to 2 pi to cover the whole surface. All right, we did that. And then we found the normal vector to the surface as partial derivative of R with respect to theta, cross that by partial derivative of R with respect to phi, right? If we found that we're not going to do that, so this will be the normal vector, and this will be the magnitude of this normal vector, which is R squared sine theta. If you calculate this, remember that becomes just simplifies down to sine theta. And then remember that the unit vector is this normal vector, unit normal vector is this normal vector divided by its radius. Is it R? Yeah, I think this should be R, not R squared. Yeah, I think this should be R. Sorry, it's my. Yeah, these are R, not R squared from before. So if you divide that by R, you get the unit normal vector, which we call also R hat, because the origin is at the center of the sphere here, right? So, and we talked about dA being the magnitude of this normal vector times d theta d phi, the magnitude of the normal vector that you get that times the d of each parameter u du dv, in this case u and v are theta and phi, and you can write that as r squared sine theta d theta d phi. Let me see, but this one is correct. It is r squared sine theta d theta d phi. So this should be r squared sine theta. But I don't see, if you do n divide by magnitude of n, that's correct, sorry. N divided by magnitude of n becomes this, which is also R, yes, this is R divided by this capital R, the magnitude. All right, so everything correct, sorry. Yeah. So dA becomes like this. And I showed you that this also makes sense. In physics, we're not doing the parameterization, but we can intuitively look at it and say that this is the element of area if you have d theta and d phi, means that increment in theta and increment d phi. If you make a small increment in theta, you get a length here that is r times d theta. If you make an increment in phi, it goes like that. You get an increment which is equal to this distance times d phi, and that distance is r sine theta. So get r sine theta d phi times r d theta. So it becomes r squared sine theta d phi d theta. So that is the correct element of area. And the element of volume will be if you are inside the sphere inside volume, dv is lowercase r squared, because r is for the surface, and when you are not at the surface, it's just r from the center, and sine r squared sine theta d theta d phi is the area times dr becomes the volume. Okay, so these are the elements of area and volume, area for the surface, and this is the element of volume inside the surface, inside the sphere. All right, so we had these before. All right, so I didn't really, I didn't want to go into details of that. Now consider the simple example of the vector field F equals to r hat. So imagine at any point, there is, of course, r hat, means that at any point we assign a vector to the point which is equal to r hat, means the unit vector in the direction of r, which is from the center to that point. If F is r hat, what is divergence of F? Can you tell me? Of course, it is, you have to do some calculations to get that. But how do we find divergence of F? So let me show you that here. R hat means what? F, that is R hat, this is F, R hat is actually R vector divided by magnitude of R, which is x, y, z, x, y, z, this is R, divided by magnitude of R. What is magnitude of R? Is x squared plus y squared plus z squared to the power 1/2, right? Square root. You can write this as x squared plus y squared plus z squared to the power -1/2 times x, y, and z. So this is now r hat for any r position vector point in space. We say for any point in space, doesn't matter where it is. If this is r, then this is r hat for that. All right. So we can write it in terms of x, y, z like that. So now we want to find divergence. Divergence means partial derivative of this x component with respect to x plus partial derivative of y component with respect to y plus partial derivative of z component with respect to z. So become the first part, which is partial of fx or f1 with respect to x is this, is partial with respect to x of x squared plus y squared plus z squared to the power -1/2 times x. And this is a product, right? We use product rule for differentiation. Becomes partial of x with respect to x times that, which is just x squared plus y squared plus z squared to the power -1/2 plus the x times the derivative of the other side. So that would be minus 1/2 times x, right? Times x and times x squared plus y squared plus z squared to the power negative 3/2 times the derivative of the base in with respect to x, which is 2x. So I write 2x squared here. So 2 cancels, and then you have partial with f1 with respect to x equal to this x squared plus y squared plus z squared to the power negative 1/2 minus the 2 cancels, you get x squared to the x squared times x squared plus y squared plus z squared to the power negative 3/2. Okay, if you do the same for the f2 with y, partial of f2 with respect to y, you get the same thing here. Minus, this becomes y squared. X squared plus y squared plus z squared to the power negative 3/2, right? And the same for z. If you add all of them, you get 3 of these, 3 times x squared plus y squared plus z squared. I think we did that before, maybe. 3 of this to the power negative 1/2 minus, this becomes x squared plus y squared. You see, they all have this factor. You can factor that. And what you get is x squared plus y squared plus z squared times x squared plus y squared plus z squared to the power negative 3/2. And this is power 1, and negative 3/2 becomes negative 1/2. And with this, 3 of that minus that 1 of that becomes 2 of those. So it becomes 2 over x squared plus y squared plus z squared to the power 1/2, which is 2 over r. All right. So this is divergence of r hat, which is 2 over r. So it depends on r. Means that the farther you get, the divergence is smaller. The closer you get, divergence is larger and becomes infinite at the origin. Okay. So this divergence of f is just 2 over r. Okay. So that's 2 over r. And now, what is the surface integral of f over the sphere? Surface integral of f over a sphere is double integral over surface S of f dot n dA. Of course, I should have put a circle here because it's a closed surface, but I didn't do that. So f dot n, f is this, and n is also r hat, right? Because it's a sphere. The normal component or normal vector, unit normal vector to the surface is always equal to r hat. F is r hat, n is r hat, so f dot n is just 1, right? So this becomes double integral over the surface of dA, the area element. So this becomes the total area of the sphere, becomes 4 pi r squared. You can also put this dA, we did that before, r squared sine theta d theta d phi, r squared comes out, you get a integral over d theta, sine theta d theta gives you a 2, you have an integral over phi, so it becomes, say, r squared times integral from 0 to pi sine theta d theta, that gives you a 2, times integral from 0 to 2 pi of d phi. That gives you 2 pi. So 2 and 2 pi, this becomes 4 pi r squared. All right. So that is the double integral over the surface of f dot n, which is the surface integral of f. On the other hand, the volume integral of divergence of f. You see, now divergence is this, and we want to integrate over the volume. So triple integral over the volume of the sphere of divergence of f dv is what? So divergence of f is this, and dv is this, right? So it becomes 2 over r times r squared sine theta dr d theta d phi. And then these integrals can be separated. 2 comes out, and you have integral over dr of r dr, and integral over theta from 0 to pi, sine theta d theta, and d phi. So becomes this 2 integral from 0 to r of r dr. Over the volume, r goes from 0 to the surface, right? That's r. So r changes from 0 to r, theta changes from 0 to pi, and phi changes from 0 to 2 pi to cover the whole volume of the sphere. And then this integral of r dr becomes 1/2 r squared. Put the limits, becomes 1/2 capital R squared. The second one becomes a 2. The third one becomes 2 pi again. So 2 times r squared over 2 times 2 times 2 pi. One of the 2's cancel, you get 4 pi r squared. So you see that these two are the same. It means that these two are the same, which confirms the Gauss theorem or divergence theorem. The triple integral of divergence of this function, which is r hat, is the same as the double integral over the surface of f dot n df. Does it make sense? So this is a very simple example that shows this equivalence, confirms the divergence theorem. Any questions? All right, let's do another example. What if f is r? If f is r, what is divergence of f? Can you tell me? This is easier.
Yeah.
Sorry, I didn't hear you. You're breaking up. Try again. So divergence of R. Yes. Divergence of R is, oops. Divergence of R is equal to its partial derivatives dot x, y, and z. The partial of x with respect to x is 1. Partial of y with respect to y is 1. Partial z with respect to z is 1. So divergence of R is 3. All right. So the surface integral of f, which is r times r hat. You see, r can be written as on the surface, the magnitude of the radial vector times the unit vector in the radial direction. So r times r hat over the surface. The surface integral is f dot n. So this is f, and this is n. So you see r hat is 1, so it becomes just r, right? So it becomes a double integral over the surface of r dA. And r is the constant, comes out of the integral, and we get integral of dA, which is the total area, becomes 4 pi r squared. With that r, becomes 4 pi r cubed, right? And now, on the other hand, the volume integral of divergence of f, which is 3, is this. That triple integral over the volume of divergence of f dv is 3 times dv. Again, dv is this, right? R squared sine theta dr d theta d phi. Again, the integrals can be separated. You get 3 times integral from 0 to r of r squared dr, from 0 to pi of sine theta d theta, from 0 to 2 pi d phi. And the first integral becomes r cubed over 3, and the second one becomes 2, third one becomes 2 pi. So 3 times r cubed over 3 times 2 pi becomes 4 pi r cubed. Again, you see that these two are the same, means that these two are the same. It confirms the divergence theorem. Okay. Any questions?
So yeah, Professor, so why are X, Y, and Z?
Sorry, why? Sorry.
Why R is X, Y, and Z?
Oh, that's what R is, right? For any in the three-dimensional vector space, if you have this, this is R, this is the radial vector. It has 3 components. The X component is X, Y component is Y, and Z component is Z.
Okay.
Yeah, it's basically it's connecting X, Y, Z is to the origin. So it has X component as X, Y component as, and this is R. So we call it position vector.
Oh yeah. Thank you.
You're welcome. All right, any other questions? All right. So this is another problem that's just arbitrary problem from the book, I guess. Find the surface integral of x cubed plus x cubed and 2x squared y and x squared z. This is the vector function. Now it's not just a r or r hat or something. It's a more complicated function over the surface of a sphere of radius r, centered at the origin, the same surface. So again, the same story about parametrization. N is r squared, and unit normal vector is just r hat. dA is that, dA is that, and dV is r squared sine theta, dr d theta d phi. It is clear that if you calculate f dot n dA, you know, this is n. You do this, you write it in terms of all these sines and cosines. And if you do f dot n times dA, it will be a complicated function of sines and cosines. But divergence of f is a simple function. So instead of calculating the surface integral, we can use Gauss theorem to calculate the volume integral of divergence of f, which is a simple function. All right, let's do that. The surface integral of f dot n dA, which is the surface integral over that sphere, is equal to the divergence of f over the volume of the sphere. And that is just 6x squared dV. And x is r sine theta, cosine phi. So it becomes 6 times, sorry, r is, yeah, is here, remember, I put lowercase r because this is for the surface, but for the volume, r is lowercase because it goes anywhere between 0 to the surface. So I put lowercase. So x is lowercase r sine theta cosine phi. So x squared becomes r squared sine squared theta cosine squared of phi, right? And then dv, which is this, r squared sine theta dr d theta d phi. So you see, we have r to the 4th power and sine cubed and cosine squared. So this becomes integral 6 times integral from 0 to r to the 4th, sine cube theta d theta from 0 to pi, and cosine squared of phi d phi from 0 to 2 pi. And we can calculate each one of these. This is the integral of sine cube. We separate sine squared and we turn it into cosine squared, 1 minus cosine squared. And then if cosine is u, then sine, if cosine of theta is u, sine theta d theta becomes negative du. So that's why there's negative sign in here. And so it becomes this integral, and then you evaluate it, it becomes 4/3. And then the other integral, cosine squared, we can turn it into double angle, 1/2 plus 1/2 cosine of 2 phi d phi. Cosine of 2 phi is periodic, gives you 0, 1/2 d phi gives you 2 pi divided by 2, get pi. Therefore, this integral becomes 6 times r to the 5th over 5 times 4/3 times pi. And you see that this 3 cancels by with the 6. So you get 8/5 of pi r to the 5th. All right. So this double integral, instead of doing the actual surface integral, it is a lot easier to do divergence and integrate over the volume. For my own curiosity, actually, I did that directly to see what the difference is. So this next page, so these two, you see, if you do the surface integral, you end up having these integrals. And you can simplify, and this becomes that. And you involve 1, 2, 3, 4 integrals, and this one is repeated. So these 4 integrals can be evaluated like that. And this one, and that one, and that one. So it, usually one is easier than the other. If you see one of them is more complicated, this seems to be complicated, you can transfer to the other one. All right. So yeah, it is hard to know basically, but from the functions you can see which one is easier. All right, so you see that it is a lot harder to do it this way. There's lots of integrals, and if you evaluate all of those integrals, then it comes to the same answer actually. Yeah, I did that in detail to make sure that you get the same thing, but I wanted just to see how much harder it is. Okay, sometimes it is much harder than this, but on the other side, the other one might be a lot easier. So for example, in the homework, if it says use the Gauss theorem to do this surface integral, you should know that if you transfer it to volume integral, it becomes easier. Or if they say find this volume integral using Gauss theorem, you know that if you transfer it to the surface, it will be easier. Okay? Any questions? So you see now, compare this, which was like 2 lines, with this. A lot harder. Okay. All right. Another application of Gauss theorem is this. Remember, we derived the continuity equation, which was showing the conservation of mass. It says that divergence of rho v, which is mass flow from one point going away from one point, is rate of change of the density of mass in that point. All right. So this was for compressible fluid flow. Now we can apply Gauss theorem to this by integrating both sides of this equation. So if you take the integral of both sides, has become triple integral divergence of rho v dv equals to negative triple integral rate of change of rho dv. But now this one can be converted to surface integral using the Gauss theorem. And on the other side, we can we can switch the order of the time derivative and the spatial integration, okay? So if we do that, we get double integral over the surface of rho v dot nda, that is the conversion of the left side. On the right side, we take the derivative out of the integral. So we switch the order of the spatial integration with the time derivative, okay? So if you do that, you see that this triple integral of rho dv, rho is the mass density, so it is dm over dv, and if you multiply that by dv, it becomes dm, and integral of all dm becomes the total mass inside. So we can write it like this: double integral rho v dot nda is equal to negative rate of change of mass inside the volume. Yeah. So this is the same thing, but it's a integral form. M is total mass inside the volume. This is the integral form of the continuity equation, which says that the mass flow rate out of any closed surface is the same as the rate of decrease in the total mass inside the surface. All right. So here is differential form, here is the integral form, the same as Gauss' law that has two forms. This also has two forms. And you can go back again from the integral form to the differential form the same way as I discussed. All right, I think it's better to take a break, and then we go to the last section, which is the new definition of curl of a vector field, which is similar to the new definition for divergence, but it is a little bit, of course, different. Okay, so let's take a what time is it? It is 12:04. Let's come back at 12:10. Okay.
Professor, real quick, could you go back to the last slide?
Sure.
Thank you.
So I'm here if you have any further questions.
Yeah, Professor, I have one question.
Yeah, sure.
I know at the beginning of the class, we see that this class has been recorded.
Yeah.
So where the classes are recorded, where can I look for them?
Oh, they are on my YouTube channel.
Okay.
Yeah, if you, because there's no, these files are big, there's no place for me to put them, so I put them on a YouTube channel. Yeah.
Okay, that makes sense now.
If you search my name on the YouTube, yeah, you get that.
Okay, so are the same lectures that we see right here, right?
Yes.
Oh, okay. So thank you, Professor.
You're welcome. Pause that for now. All right. So, new definition of curl of a vector field. So we have the curl previously defined like this, with the determinant of ijk, the partial derivatives, and the components of the vector. Using concept of line integrals, we have a new definition of curl of a vector field. At any point P, the component of the curl of the vector field F along the direction of the unit vector n is defined as the follows. See, this is point P. We want to find curl at this point, but curl is a vector. We want to define the component of the curl along this unit vector at that point, from that point. All right. So this is the way we define the curl. On the plane passing through point P and perpendicular to n, we choose a small simple region S containing point P. And this is in the plane of perpendicular to N passing through point P. In that plane, we take a small region. This is area region now. We call it S. And the boundary of that, we call it C, and we calculate the integral of the vector field F over the closed contour C, that is the boundary of S. So we calculate this integral over the closed loop or closed contour of C of F dot R prime DL, or F dot DL as a vector, or R prime. Remember, if R is the position vector on any point on C, the tangential vector is R prime, and if you multiply that by DL and you make a small vector tangent to the curve C, and then calculate F dot that little piece becomes a scalar. If you add all these pieces together, you get the line integral over the closed path. Then divide this line integral by the area. If this has area A, we divide that by the area of this S. All right, and then take the limit of this quantity as S shrinks down onto P. So this piece shrinks down here so that the maximum distance D of S of the points of S goes to 0. All right, so we take a limit as D of S goes to 0. If that limit exists, we call it the component of the curl of F along the direction of N at point P with coordinates X, Y, Z. So that is the curl of F dot N, means the component of the curl of F along the direction of N at that point, or curl of F along N. There are different notations for that. All right. Now, is there any questions about this? Again, this seems a bit complicated, but it makes a lot of sense. And from this definition, you can just look at some vector fields in, if it is visual, you can say whether it has curl or not, and which direction is the curl. So from this definition, it's easy to derive the Cartesian representation, that you see above. So how do we do that? Let's do that first. Consider the Z component of curl of F, which is curl of F in the Z component, which is third component, or curl of F dot K. So this is K hat, unit vector in the Z direction. So in order to do that, we can take a plane that passes through a point and is perpendicular to K. So it is parallel to XY directions, right? And then calculate this quantity as the area shrinks. So that is approximately equal to 1 over the area, as so instead of the limit as ds goes to 0, we take for a small area and we say it's approximately correct. And of course, then after that, we do the limiting. So here is the situation. Now we are in XY plane, which is the perpendicular to the Z direction or K direction. And we take a small loop. We want to find, let's say, the component, Z component of curl at a point here. That could be this point, could be any point, but this shrinks to 0 anyway. So if C is the rectangle in XY plane with size delta X, delta Y at point XY, we have this. You see, the third component, according to that, is the line integral over this area, this path, right? Which is C. And divide by the area, which is the delta x, delta y. Okay, so I'm doing this. So how is that? So I'm saying the area, sorry, the line integral becomes this numerator. The denominator is just the area, delta x, delta y. So how is that the line integral? All right, first we go from here to here, calculate the line integral. So because this is small, we say that this will be the x component of f evaluated at x, right, and y, times this distance delta x, right? And then we come here, we say that this part will be the y component of f evaluated at this point, which is x plus delta x, and y times this distance, which is delta y. So I say f1, x and y, delta x, plus f2, x evaluated at x plus delta x and y, times delta y. So we have these two. And then for this one, we evaluate x component at the position x and y plus delta y, which is this one, this point, right? And multiply by delta x, and it's negative. It is negative because we're going in the negative x direction. X plus delta x, y plus delta x. No, we don't. It says x plus delta x and y plus delta x. No, see, you can, this area is very small. Delta x and delta y are very small. So for here, because it is small, we can take the value of f at any point here. So for this one, we take the value of f at this point, x and y, but x component, and times delta x. So that is just basically f dot dr over this part. And then for this one, we evaluate the f at this point and the y component of it times delta y. So that is this little piece here. And then for this one, you see delta y is this way, going, sorry, delta x is going to the right, but we are going to the left. So there's a negative sign. And the x component of f evaluated at x plus x and y plus delta y, and it means at this point. And then coming down here, you can use the value of y component of f at this point and multiply by delta y, right? And it's negative because we're going down. All right, so we have all these, and then we can write it in a different way. You can put all the x's together like this one, and the y's together like these two. You said, yeah, Ian says your y coordinate point says y plus delta x. Oh, yes, that's a typo. Thank you. Yeah, it should be delta y plus delta y. Yes. Thank you for mentioning that. I didn't see it before. Yeah. So yeah, this one is y plus delta y, means this here, this point here. But we are not using that point anyway. You're using these 3 points. All right, so we put delta x and delta x together, and we factor a negative sign, and we put delta y and delta y together as well. So this becomes like that. So this one becomes negative f1 x and at x and y plus delta y times delta x, minus this, because there's double negative here, becomes plus f1 of x, y, delta x. And then we have this part minus this one. All right. And now you see here, delta x can be canceled. Here, delta y can be canceled, right? So what we get here is f1 of x and y plus delta y minus f1 at x and y divided by delta y. This becomes f2 at x plus delta x and y minus f2 at x and y over delta x. And see this delta x here, delta y here. And then if you set delta y and delta x going to 0, this will be the partial derivative of f2 with respect to x, right? And this one becomes negative partial derivative of f1 with respect to y, right? So it becomes like that. As you see, it's curl of f in the third component, which is z component, is this, which is the value that we expect. And if you do the same thing for the second and third component, first and second component, you get similar result. All right, so this shows that from this definition, we can go to the other mathematical definition. That's not easy to see things, you know, it's just the math and it's very boring. But here you can see what it really means. Okay, that's why I'm saying it should be taught this way. But it is, of course, takes some. You need to know the line integral, surface integral, and all of that. All right. So what is the Stokes theorem? Now, similar to Gauss theorem, we have the Stokes theorem. Let's go to get the Stokes theorem instead of just expressing it the same way we did before. Consider an open bounded surface S, whose boundary is a piecewise smooth curve C. So it's it is a surface. It doesn't have to be flat surface. It was hard for me to draw it here, but it can be any surface, like a hat, you know, that has, you know, some surface, or a fishnet that has a round boundary, which is the circle, and the boundary is piecewise smooth, and consider the vector field F to be a vector function that is continuous and has continuous partial derivatives in some domain S, in some domain that contains the surface. All right, so these are the formalities that we are using implicitly, so these should hold. And then assume that the surface S is subdivided into a large number of very small rectangles of size du dv. You see, du dv is delta u delta v, is that if you parameterize the surface by two parameters u and v, then you can change the delta u delta v, right? And get this surface areas on the surface. The figure here shows this surface and subdivisions. Of course, this could be in space, that is now two-dimensional, but as I said, it doesn't mean that the surface is flat. It could be any surface. All right, let's focus on subdivision K with boundary CK of that rectangle, and then the line integral of the vector field F over the boundary CK of this cell. The line integral is that, is integral of F dot R prime dl over the boundary of this cell, going counterclockwise. All right. From the new definition of curl, this is roughly equal to the normal component of the curl of f at the point in that rectangle. So remember, curl of f dot n was this. So if the area is small enough, we can take out the limit and say roughly is equal to that, right? And then this integral over this path, which is almost rectangular path, becomes the component of curl perpendicular to the surface at that point times the area. All right. So we can write it this way. So the integral becomes the component of curl at that point, which is that point in space is has coordinates x, k, y, k, z, k, some point in that surface. Doesn't matter where it is, somewhere in there. We take a point and we call it coordinates x, k, y, k, z, k, and the area of that piece is delta a k. And so we have this equation now. It's an approximate equation because we are not at the exact limit, but the smaller it is, the more accurate it is. And we are going to shrink that to 0 anyway. So it's we can work on that. All right, so we have this this equation now. So according to the definition of surface integral over S, sum of all of these on this left side over k from 1 to n as n goes to infinity and norm of delta ak goes to 0 gives this. The surface area, the surface integral of curl of f dot n dA is equal to limit of sum of all these quantities. See, curl of f created at a point in that kth cell or area element dot the normal to the surface times the area of that cell, which is this. So adding all of these and k going from 0 to infinity to 1 to infinity, as the number of cells go to infinity and each one of the cells goes to 0. So this is the surface integral of curl of f dot n dA. All right, or surface integral of curl of f, I should say. That dot n dA is just the normal component taken over the surface. So, and this can be written as the limit of, according to this will be limit of all of these line integrals, right? So because each one of these is a line integral over around that cell. All right, so let's work on this. So far we have this surface integral of curl is equal to sum of all these line integrals. That comes from the new definition that we have. All right, so let's work on that. But the same way as we did before, the line integral of f over each side of cell k cancels with the line integral over the side for the cell on the other side. So again, to illustrate that, this means that, for instance, the line integral going up over the right side of the green cell, means this one, when we are calculating the line integral over this green cell, is the opposite of the line integral over the same side for the yellow cell going downward, because we're taking the line integral for each one counterclockwise. So for this one, we go up on this side. For this one, we go down on the same side, right? So you know that the line integral, if you go one way or the other, they're opposite of each other exactly. So when you add all these contributions, so these two cancel out, and this one on this side cancels with the same side on the other one, and this one and this one, all of them cancel out. So the same is true for all the cell boundaries within this contour C. All right, so all of these internal line integrals cancel out, unless you get to a cell whose there's no cell on the other side, right? Then that part doesn't cancel. This one doesn't cancel. So the whole sum of all of these become just the line integral over the boundary. Sum of all the line integrals over all cell boundaries is equal to the line integral over the exterior boundary C. Does it make sense? I hope it does. Therefore, the surface integral of curl of f dot nda equals to the line integral around the boundary of the surface of f dot r prime dl. All right, and that is the Stokes theorem. All right. So we have Gauss theorem and Stokes theorem. These are very important in vector fields. And now let's see what we can do with this. One example from physics is Ampere's law. You know, the integral form of Ampere's law is this. In electromagnetism, you learn that the line integral of the B field over any closed path is equal to mu naught times the current, electric current passing through that path. All right. So we can use this. We can use the Stokes theorem to change this to differential form. If we write the total current as the surface integral of the current density J over the surface bounded by C, we have, so any surface that is bounded by C, the current that goes through this should go through that surface. So we write the current as the surface integral over that surface of J, which is the current density. Current density is current per unit area. So instead of I enclose, we write double integral of J dot NdA, which is the flux of current going through the surface. On the other side, we can write integral over the curved surface can be transferred into the integral over the surface like that. So according to a Stokes theorem, the left side is the same as the surface integral of the curl of B over the surface S bounded by C. So we can do this. And because the surface is arbitrary, it is true for all the surface, since the surface integral over any surface, we can conclude that the function under the integral signs are the same at any point. So we can conclude curl of B equal to mu naught times J. Remember that we talked about that before. I had an example that showed that. Of course, that was just an example. But anyhow, this shows the integral form of Ampere's law has a differential form that's exactly equivalent to that. All right. Any questions? So you see that in physics, there are lots of examples that vector fields are involved. And that's why at the beginning, when I learned these things, and it's always easy for me to understand all of that. And so that's why I want you to learn these, and then your life will be a lot easier if you're going to higher level physics or engineering. Any questions? Yeah. So differential form of Ampere's law. And we can go back from differential form, to the integral form. All right. The same way, we just do the opposite. All right, remember we had in section 10.2, we had path independence of line integrals. We put forth 4 different conditions, and we said that they are equivalent conditions for path independence. And we talked about this and this. They were, the equivalence of them is obvious here from this equation. And then I said that we don't get the curl of f equal to 0, the relevance of curl of f equal to 0 with all of these, and we learn it, we will find it from a Stokes theorem. Now we have a Stokes theorem, and you see, we can see that this is equivalent to that, which is equivalent to path independence. So let's see what the curl has to do with path independence. Suppose curl of f is 0 for every point in a region of space. Then for any surface S, the surface integral of curl of f is 0, because curl of f is 0. And then from the Stokes theorem, the integral of curl of f dot n is the same as the integral of f dot dr, which is the line integral over any closed path is 0. Right? Now consider 2 points A and B and 2 different paths C1 and C2 from A to B. So from A to B, you can go this way or you can go this way, right? We take closed path C to be the curve C1 from A to B plus negative C2 from B back to A. So we go this way and come back from the other way. We have, according to this, curl is 0, the line integral over any closed path is 0. So we have that. And then we can split the line integral into 2 pieces. One is on C1 and the other one is on negative C2, means that we're going on C2 in the opposite direction. And we said that if you go in opposite direction, you get a negative sign. So it's the same as going on C2, but we get a negative sign. And that, if you move this integral over, becomes the integral over C1 is the same as integral over C2, okay? So the line integral is path independent. So for any path, 2 paths, you can do the same thing and show that the integral is the same on any paths. So the reverse argument is very easy, because if you assume path independence, you conclude that the line integral around any closed path is 0, and then from the new definition of curl, the component of curl are 0 at any point in the region. So the integral, if you have path independence, you get the line integral equals 0. All right. I guess that's it for today. This is the homework for today. I have put it on Canvas already. This is for next week. And there is a quiz also. All right, should stop.